Okay, so thanks the organizer for having me for this nice workshop for such a long time. It's really a pleasure and enjoy such environment. And thank you all of you for being here today. So today I'm gonna have 1/3 on the Blackboard, motivational part on the Blackboard, but then I switch to slide because otherwise there are pictures impossible to draw for me. I hope you don't mind, but so today I'm going to talk about these ideas about thermal entropy and entanglement transition using modular objects that I've been working on with my collaborator that are here. So Michael Minchev, my long-standing collaborator from Pisa, and Domenico Seminara from Florence. And then Stefania Cagioli was a PhD student in Florence. Francesco Gentile is my PhD student in SISSA, who is finishing now and applying for a postdoc position. And Andrei Rotaru is a postdoc in SISSA. And yes, I thank all of them because without them, it would have been impossible for me to do this work. Anyway, let me motivate a little bit these studies. So I'm going to talk about entanglement. So everybody knows what it is. So you start from a Hilbert space, and the state is a density matrix. This can be pure or mixed. This is important for us. Okay. You're used to this ground state. We're going to talk about thermal entropy. So our system can be also in a mixed state. And then you assume that your system is spatially bipartite in some way, in this way, and then you introduce the entanglement entropy in the usual way as a von Neumann entropy of this object. Okay, this is wait. First, of course, you have to trace over B, and this is the called reduced density matrix. And then the whole point of entanglement is that even if you start from a pure state, this object is going to be mixed, and so it's natural to compute the von Neumann entropy. So this is the standard object that you work with. But today, motivation of this is that I would like to push you somehow to think about properties, features. So entanglement, is not only entanglement entropy. So think about the feature of entanglement. That are not captured or easily captured by entanglement entropy. Okay, so we like this quantity because it's scalar, it's easy to calculate, it has very beautiful properties, but entanglement is not only this one, so there are features that maybe can capture using other objects, okay? I want to give you two examples. Of course, this is very complicated because, for instance, it's part of the motivation that recently people talk about complexity. And the slogan of Saskin is that entanglement is not enough, meaning that entanglement entropy is not enough. And so you have to necessarily think about other quantity to explore entanglement. So yes, that's a good question. Enough, what is, at least in my hope, is maybe when you can catch all the microscopic data of your model from entanglement, for instance. So suppose that working with entanglement, you can, for instance, if you compute this in CFT, you catch the central charge. If you work something else, you can get other data. That's, I think, is the idea of what now Davis called entanglement bootstrap. So extracting microscopic data from entanglement property. And then maybe, in an experimental side, working in this kind. But from the theory point of view, would be nice to have some tools to probe microscopic theories using typically non-local object or microscopic. That's maybe enough. But if you take this point of view, clearly this is not enough. So the example I'm gonna give today, one is related to thermal entropy.
If you look at generic manifold data, it would be saying that features that grow for time.
Yes, great question. So the second example I'm going to be precisely in quantum many-body. I don't know in QFT, so yeah. Yeah, yeah. There are many examples. I just put the stone into the lake. So give you two examples. So one question that I think captured this idea is the thermal entropy, namely thermal entropy versus entanglement entropy. So you know, even one of the motivation at the beginning that brought people like Bombelli, Sorkin, Srednikin in the 80s to talk about entanglement was to understand a black hole entropy, which typically has a thermal nature. And so at the beginning, the motivation was to understand this kind of thing. But now we have a lot of knowledge. So but still, the relation between these two quantities to me is not completely clear. Let me give you an example. 2D CFT that at finite temperature, no? A standard situation on the line, and this is the interval A of length L. What is the entanglement entropy of this situation? C over 3 log beta pi epsilon sinh pi L over beta at finite temperature. Beta is the inverse temperature, L is the length of the interval, epsilon is the UV cutoff. This formula has been found by Cardi and Calabrese using twist field method, but for the moment, let's focus on this result. If you see, you go to high temperature, okay? High temperature, it's immediate to see that if you catch the exponential from here, you get S comes C over 3 pi L over beta. And this is the thermal entropy, right? Is the Gibbs entropy of A. Stefan Boltzmann law for 2D CFT, studied by Cardi, Affleck, Ludwig in the 80s. You see, but now, so Stefan Boltzmann said that there is a thermal density related to central charge, which is precisely, this is what they found in the 80s about the thermal entropy in CFT, studying CFT at finite volume. But now, from this formula, consistency check of this formula was that at high temperature you get the thermal entropy. Okay, so thermal entropy of what? Of the subsystem, no? Because it is a volume law in the length. So this is a kind of relation. So this is a concrete relation between entanglement entropy and thermal entropy that I would like to discuss better later using other objects in the philosophy. The second thing is related to what I call entanglement transition. And what is an entanglement transition? Let me give you a famous example. Nice example from ADS. Yeah. Yes. From here, now later, if you wait, I have a, yes, you can find information about the spectrum, but later if you want, if you ask me the question later, maybe. For the moment, I just want to say that it is nice relation between the exact formula CFT and in high temperature, which is natural because we expect that at high temperature everything becomes classical, the quantum model becomes classical, and so the second thing is related to this entanglement transition, and what it is everybody knows what is a transition. So you expect some discontinuous behavior in some entanglement quantity. And let me give you the example from the SIFT. So from the SIFT, you know that there is the famous Ryuta-Kayanagi formula saying that if you have, for instance, this is an example, ADS4 at fixed time, this is the holographic direction. So you have your region here in 2 dimension, and entanglement entropy holographic is area of the minimal surface attached to the region. Okay, so this is the gamma A hat. Now this is called Ryuta-Kayanagi surface. It's simply the minimal area surface attached in ADS or asymptotical ADS attached to the boundary of A, which is homologous to A, but for the moment. So what if you consider the case of 2 disjoint region, okay, and you apply this formula, it's clear that you have a transition in the distance between the 2 regions. In particular, if the region are very far, you expect this kind of behavior. If the regions are very close, you expect this kind of behavior. So here there is a critical distance. Okay. And there is a transition in the entanglement entropy. Okay. So this transition is very famous. It's in the context of Wilson loop. It's called the Grosso-Guri transition. But in the end, it's just the fact that at the classical level, so when you have this compute this area, you have 2 solutions that compete, and at some point they are equal, and after below this critical distance, this one win. Another equivalent way to say is to introduce the mutual information that somebody has talked about. Okay, this is a UV finite quantity because this combination guarantees that the divergent piece coming from the area of the 2 regions cancel. So this is UV finite. Okay, and if you plot this quantity for this holographic system, you see that in terms of the distance, for a small distance is positive because this surface win. At the critical distance becomes 0 because this solution wins. So you have a transition in this way. So this is my, importantly, if you calculate the same quantity into this CFT, I find that C positive, there's no transition in A. So if you calculate for simple model, you can do for a free fermi or free boson, you can calculate this quantity. You don't find this quantity has a beautiful power law decay, and so this transition is an effect of large C limit or large N. Yeah, if you are decoupled, yes, if they are decoupled, you don't see anything because they are decoupled, but you need strong interaction, yes. yeah, let's say strong coupling. I just want to point out that, as far as I know, the origin, the CFT derivation of this is not fully understood. It's a signal. It's a signal of. It's a feature of this holographic entanglement entropy that is difficult to catch from a purely CFT calculation. That's what I mean. So. No. I'm just saying that in simple cases where we know analytically this object, which are very few, you don't see. But yeah, it would be nice to find a. No, I'm just saying that this large C is based on this formula. So this formula, this is valid holographic at large n. Yeah, as far as I know, I don't know any CFT thing that show that, okay, you have some. Yes, of course. Yes, these. Yeah, you get at large C. Yes, you get the identity in the channel, but. Yeah.
So I don't know about this particular example, but usually in holographic examples, that's what you use to get the charge. So you just always assume that like a relevant correlation function is dominated by like
Yeah, the point in. So there are calculations with twist field, okay, and then calculating this object, and then imposing, assuming that in this OP on the main contribution at large is given the unitary. Then you get, but let's say if you ask in higher dimension, which the transition is still there, and it's also depending on the shape of your surface. That's a complicated problem still there. So. Sorry, yeah, this twist. Yeah, I didn't talk because. Right. No, it's continuous, but the derivative is right. So this is a motivation. So just an example of a transition that is captured in this way. This transition is captured by mutual information, but the one I'm gonna talk is in this thing. So okay. So we are not. Yes. Yes. This PCR. No, this formula. Yes. No, you're right. Now here you have to assume that, of course, the order of the scale of the epsilon is such that this is the leading piece. So yes. Here, if volume is infinite, finite volume in L, you mean? Yes, maybe. Yeah, let's say that this, what I like about this result is that it's universal. When you go, maybe if you do the same calculation at finite volume also, infinite volume, yeah, no, okay, you keep this next order. So what? Yes. Yeah, which is extensive here. There's no finite volume here, it's infinite volume. Ah, yeah, okay. Yes, yeah, let's say here you have to, there is L over beta, there is L over epsilon, so you have to put some order here, no? When you do this calculation, anyway. So this is just a thing, so, but the point that I want to make is that if you want to, what happens if you, so if you look at more complicated object, so in these two examples, you focus on this quantity, but if you go up this direction, you have, you can consider this guy here instead, and this is a density matrix, so it's a positive definite. You can introduce this operator, you can take the log, this is called modular Hamiltonian or entanglement Hamiltonian. Okay, it depends that people in ConMath community call like this, people in QFT call like that, but it's this object. And this is, of course, the operator that give you the entanglement entropy. So if you know this, you know everything, basically. But you can say, okay, there is so this is the highest level of information about bipartite entanglement. But you can say, okay, compute the spectrum of this guy. It's called entanglement spectrum. And out of the spectrum, you calculate an entropy just from the definition. Okay. So there is an hierarchy of information here, and this is a scalar, a function of the spectrum. So the point is that if I go up, can I get information, more information? So can I see some features that are not captured by this guy, which are instead captured by these two? That's the question. And then I wanna put here another object that I will discuss later, which is called contour of say. And this is the standard problem. I mean, in QFT you can formulate that, but if you have finite number of degrees of freedom, like on the lattice, for instance, this becomes matrices. So you are asking if I know the matrix or the eigenvalues or the function of the eigenvalue, which information I lose in this procedure of tracing out things. And this quantity here is in the middle because it involves the eigenfunction and eigenvalue. So so this one, so that's to me the hierarchy. Think about. Okay. Yes. Ah, yeah. Contour of entanglement entropy. It's a contour means it's a kind of a density. So this is the idea that can I write SA as an integral of SA of x, a kind of a function that give you the spatial distribution of entanglement, if it's reasonable. How you do that? That's what is called contour of entanglement entropy in the literature. So in order to do that, I'm gonna use tools from algebraic QFT, and in particular what is called Tomita Takesaki modular theory. that's why this word modular is in the title, modular object. And I briefly tell you what I mean, and then we'll switch. So the point is that so people in algebraic QFT like to be in Lorentzian systems. So the simplest situation to think about is this right wedge, well, left wedge. So now you are in Minkowski, T and X, okay? And your A and B is positive X, negative X, okay? So in algebraic QFT, it's important to have causality, like in any QFT, and you know that things that commute a space like this, and they commute at space like distance. So you focus on the algebra of the observables here, which is called A, for instance, and then the commutant is the A prime, are the observable here. This is the example, but so what you do is that you consider the Hilbert space. This is the Hilbert space of the full theory, H, okay? And you consider a state which is cyclic and separating. This means that if you apply, if you take, now A, curly A is the algebra of the observer here, and if you apply all the operator in the algebra to this state, this is dense in H. This is the meaning of cyclic. Separating means that if A is, if you act for with an element here, this implies that A is 0. So that's the meaning of. So these are important assumptions, but you can think that your ground state satisfies these properties. Okay. So if you have this assumption, then in this Tomita-Takesaki theory, you introduce this operator. So this means that you take the algebra of the operator here acting on the state and the same thing. So here, and this operator is linear and act like this: S O omega is equal to the dagger. Okay, so a simple operation. Take the operator that associate to any operator that is Hermitian conjugate. Okay. Yeah. So these are what I call A and B are the spatial region, right? But now you have to think of the causal. So these are the algebra of observable in WR. Yeah. So people in algebraic QFT think a lot in terms of these regions in space-time because they want to keep causality explicit. And so if you do that, this is an example, but A can be any region. If you introduce this S, which is just the Hermitian conjugate, which is called in this literature Tomita operator, then you can yes. Yeah, exactly. So this is a part. It's a theory inside the big thing of algebraic theory that play around with this object that I'm gonna tell. So why? That's why. So yeah. Yeah, the motivation is that this object give you a QFT based to this row A to this one. Yeah, that's now I'm trying to, but yeah, if we are you are used to think in this term, but algebraic QFT people thinks in this term. So it's important to understand the property that they found, how they are applicable, and so the key object is this one, this operator, that can be decomposed in a unique way. This is a polar decomposition of an operator. This is a unique, and if you like to think about a similar thing that everybody knows, the polar decomposition of a complex number. This is a phase, this is the module. In a functional analysis, this polar decomposition allows you to split the operator as a product of these two guys, where delta is self-adjoint positive and unbounded in general, and J is anti-unitary. So
why does it matter? If it's delta times J, I'd say, okay, I understand why you're doing this. But now,
yeah, because S as dagger is delta. S as dagger is delta. That's the rationale of having this. It's my understanding. Yes, that's the only motivation. Yeah, if you do S as dagger, you get delta. So it's yes, dagger. In any case, it's like you say ZZ bar equal modulus. So it's modulus square. So yeah, maybe it's clear now that because this is the formal definition, of course, and then you can play around with this property. But let me give you the name first. So these two objects are the modular objects we play with, and delta is called modular operator. J is called modular conjugation. Okay. And you can say, what do they do? Of what? Of the pair algebra and state. So these operators are associated to the algebra and to the state you start with. Okay. So why you can say, there is so this delta and J preserves omega. Of course, this means that if you act omega, find omega again. But the key property is that what happens now, the point is that this object delta is positive and naturally define an evolution. Okay, so you can take an operator in your algebra and you introduce the evolution with delta. For a tau real. So in physics, you right, the natural thing is that you usually are happy with this, no? EH. This is the evolution, the standard evolution, unitary evolution with physical Hamiltonian. No? Now, if you have A and B and rho A, it's natural to introduce this object and define this evolution, which is called modular flow of O generated by kappa, if you want. Kappa is because this delta, you can write it as e to the minus kappa, because it's positive. And then you think about this kappa like an Hamiltonian, no? Like in the same way you think to the time evolution, now you think about this modular evolution with something that depends, now is what is, there are many differences between these two kind of things. One thing is that this guy is independent of the state. It's an operator, I give it Hamiltonian, and so you define this unitary operator. This delta depends, you see, depends on the state you start with. So if you start with a ground state, you have a delta. If you start with an excited state, you have another delta. It also depends on the region. But it's a unitary evolution, perfectly fine. And that's why I call tau here real is not t. Not, because you also have t in the game, no? Because t, the physical time is there. Okay, let me give you a, yes? Right. Yes, that's it is related to, it's not related to what we call modular invariance. This is not related to that. It's related to something in functional analysis, because there are modular forms in functional analysis that do something, and these in functional analysis extend this kind of, yeah. I looked yesterday in Wikipedia, and because I was explaining some question, and yes, but it's related to functional analysis. There are, because there are these modular form, and this object, it comes from there, not from CFT, of course. No, yes, there is a.
Yeah, exactly. So there's some modular.
Yes. No, yes, this is my fault. I should have studied better. But if you ask.
The way I split this is coming from Baxter, actually. And Baxter was looking at entanglement spectrum from classical stock methods.
Yes, you will see that appearing. Mm. Yeah, so let me say that this object here, this k, so now I cancel, but this rho a now is e to the minus ka. This is in the literature is called full modular Hamiltonian, because it acts on the entire thing. It's not only in A. And roughly speaking, it's useful to write K as Ka on 1 acting on B minus 1 acting on A, KB. So it's important that these operators are not, algebraic QFT people think in terms of the bipartition of the two systems, so they don't trace out part and then forget about the rest. They keep both, and that's very useful, because let me, okay, the key point that I want to make is that sometimes delta, there is a key property which is called Tomita-Takesaki theorem, which tells that if I take now this delta and I evolve tau inside my A, I stay in A. And if I evolve, maybe the minus, and I evolve in the commutant, I tau, I stay in the commutant. And then the other property, if I do the same with J, actually I change, I go to the commutant. This is a property, this is a theorem, so this is a commutant of A prime. Okay, this is a theorem. The key theorem of this, yes? Yes.
Sorry, capital delta. You know, what is that? You said it's now the whole Hamiltonian, so we're not talking about an entanglement anymore. But I was thinking, okay, this is the entanglement. This is the reduced density matrix.
Yeah. No, yeah, if you want, what the reduced density matrix is here, but there is also the reduced density matrix in B. Why not? And these combine both of them.
So what's the delta that's about to erase there?
Delta is E.
Oh, it's an S. So what's an S?
Sorry, S. Yes. S.
Oh,
sorry, yes. Yes, too many S. This is an operator, linear operator that associate an operator in A. It's Hermitian conjugate. So
that's all.
That's all. A goes to a dagger. A.
Good. Okay.
Yes.
And what does this have to do with reduced density matrix?
Yeah, the point is that this algebra knows about the bipartition. And then this S, if you want, knows also about the state, because you act, as it's defined, it acts on the state. So all the states that are generated by the algebra of the subregion. So you restrict to that. And if you apply the dagger, you stay inside. This is natural. But then if you, this polar decomposition of this operator knows about omega and the bipartition, knows everything. Why? Now, this is an analogy. This is this thing is unique in functional analysis that I don't know. So if you give me any operator, you can always find a unique way to decompose. So no, in the end here is just a definition of K. If you buy this delta and you believe these properties of Tomita Takesaki, then here there's no K, but since it's positive delta, you can define K as minus the log of delta. Just a definition. Yeah, because this is a connection with what we are used to, in the sense that, I know, but if you look at this literature, they just work with delta domains. Yeah, let me give you an example, maybe. So the example I'm gonna give is this one. So here, but the last comment I wanna relate it to what, yes, I can cancel here. Yeah. Sorry? Modular forum? No. It's just for beside this relation with modular that Alejandra asked about, take them as a definition, okay? So what I want to stress is that sometimes delta and J has what they call geometric action. Geometric action means that I can see geometrically what they do. Example. So this case, okay, which is related to the so-called Bisognano-Wickman theorem. So this case, in the ground state, for any Lorentz invariant QFT, even massive, whatever, if you take delta, you ask what are you doing here? This means that you take an operator here in a point, and you evolve in this way. So this is the tau evolution of an operator which is initially sitting here. So if you write what this delta does, this is a tau evolution, because why you can do that? Because in this case, k is equal to 2 pi x t00. So this theorem tells that in this case, so when A and B, you can write explicitly this k, and this is the boost, no? This is the boost, notice the in R, okay? But you can split this in this form, and see that Ka is equal to 2 pi 0 is the energy density, okay? So the Bisognano-Wickman tell that in this case we are lucky, you can write it explicitly in terms of the energy density, and if you sit down and study the modular time evolution, you discover that this is the thing. What happens if I start here? Well, if you start here, you do that. The complement. But then there is also the other. So this is the geometric action of delta, okay? But then there is the geometric action of J that is like a parity symmetry. So it associates one point here with minus here. And so in this example, this application of this theorem, right? You evolve in A, you stay in A. Evolve in B, you stay in B. While if you apply J in A, you change and you go in the commutant. Here, you mean? No, it's not. It's nothing. Yeah. No. It's this is A. This is the commutant. So this is what you do. You stay there. Yeah, that's okay. This is the and this talk that. Yeah. So this talk, the comment is that this talk. My claim is that delta and J give insight about the problem number 1, problem number 2, related to thermal entropy and entanglement transition. And I'll give you example now in CFT2 and ADS CFT. And this case in the lattice. So they are pretty different, but the philosophy is the same. So this is the end of my. If you have some question about the general thing. Yeah. Full case is positive. Full K, yes. Yeah, full K delta is positive. K is not positive. Is unbounded in general. K, that's why it's not an Hamiltonian. Yeah, this is another different. Thanks for asking. Yeah, this K, the point is that this K, I will show example, knows about the state you're started with and the bipartition you're started with. Okay. Yes, yes. Then there are issues that I will show about when you analytically continue. If we start. Okay. Is it okay? Right. Yeah, sorry, this is repeating. Yeah, so this is the same summary of what I've been telling you. So this is the typically people call this one parameter family of endomorph, automorphisms. This is the language that algebraic QFT people use. Yes, this is summary, but this is summary what I've been told, and now I want to tell you something about modular conjugation. So this J in into DCFT. Okay, so this is the Bisognano-Wickman that I mentioned, and in this case is the energy density T00, sigma tau and J as the geometric action, which are the Lorentz boost and reflection. Okay, this is the case, and importantly, this theorem is true for any Lorentz invariant QFT, so with mass, everything. Okay, the best situation you can think about. Now, if you go to CFT in D dimension, you can use the power of conformal maps and map this half plane into a ball of radius r. This has been done long ago by Islop and Longo, and write this operator, okay, which determines the evolution inside this thing, causal diamond. And then if you restrict in 1 + 1 dimension, it's just this parabola, when L is the length of the interval. People study the most generic, let's say, cases where this function here becomes a function that knows about if you have a thermal state or find all the possible configuration that you can do with conformal mapping. But let me stress that there are important cases where Ka is not like this. This is a local expression, just it's not one we are used to, but in many cases, K is non-local and also model dependent. This one is model independent in the sense that T0, if you have a CFT, T00 is a CFT. But things that are known in the literature, this is the most famous example by Casini and Huerta, is the case of a massless Dirac field in the ground state when A is 2 disjoint interval. In this case, you cannot write in this form. Okay, but if you do things in this form and you go to the Euclidean, you can take the Euclidean approach and say this is the interval, this is the rest. Now you introduce a UV cutoff in this way, you cut a little circle, you map this geometry into the cylinder, and then you compute the entanglement entropy in this way. And in the spirit of doing something better with respect to entanglement entropy, let me tell you that in this approach you can read off the entanglement spectrum. This entanglement spectrum, this goes to your question, Matt. So you see entanglement entropy knows about the width of this cylinder, which is infinite, only here. These G and GB are the Ludwig, half-flat Ludwig entropies associated to these two boundaries. But if you take this approach, you can read off the J, which are the entanglement spectrum, and they know about central charge, the UV, the regularization here, and also interestingly about the dimension of the BCFT associated with it. This was observed by Lochley in 2013 numerically first. It was studied the entanglement spectrum and observed that, look, spectrum is a BCFT, is not a CFT. And interestingly, if you take differences of these objects, they're called gapped, entanglement gapped, you find UV finite ratio just from this formula. So this goes in the spirit that beyond entanglement entropy. So if you look at the spectrum, you see the CFT spectrum. So in this bootstrap program, okay, look at the spectrum and you read off the conformal dimension. Now, is the half-flat Ludwig associated to this boundary here? Ah, yes, no, G, no, yes. G here is the gap, it stands for gap. Half-flat Ludwig, yes. Sorry, you are right. This is, I put it later. This G, right, is log of this. Actually, I also forget sorry. This G is the difference between these two, sorry, yes.
Depends on the size of the
Yes, exactly. So according to this calculation, depending, so the UV dependent information enters here. But if you go to the yes, precisely, yes. People study this function numerically on the lattice, and they saw that the BCFT, because when you cut, it's not obvious which kind of. Apparently, Neumann is the choice, but, but I don't know. Yes, but you are right. Thanks, Giuseppe. It's my mistake. I put yes. This G is the difference between minus log R and the smallest one. From this formula, you see that the first dependence, so you cancel, and then the ratio you cancel also this thing.
when you say Neumann, probably would get a different choice and
No, here this is a BCFT expression that you find for using maps. But then when you go to, you compare with lattice, you see that's yeah, the lattice implicitly, I don't know why, show Neumann. But then recently people study various things. When you put an operator here, there is related to symmetry, but this is another.
in the CFT, like continuous CFT, you could explicitly like defining the other.
Yes, no. Yeah, in your talk, Andreas, you used a lot this map with the CF. It's very. Yeah, this is the simplest setup, the ground state. Yeah, this is, let's say this is generic A and B, saying that A and B, in principle, you can have different. In this case, A and B are equal because. Yeah, little a and little b are equal because the boundary condition you put here is equal to this. But you can do, for instance, if you do this case, which is the one that also Andreas talked about. No, this is A. In this case, you apply this machine, and now this is GA, and this is the real Afflet-Lugul one, G boundary, okay? And this formula applies just with a different W, it's 1/2. You cut this cylinder in half and you put a physical bound, but the game is the same. Okay, but okay, I have to speed up, sorry. Yes. Yes, thanks. Yeah. Yes, yes. In the way I will show you now. This is the example. So this is the interval minus RR. So it's the most stupid example in the ground state. This is the map. You map from the complex plane. You go to the unit disk. You go to the cylinder. So you have to identify this edge with this. And if you write this map, you get. If you start from the physical Hamiltonian here, physical Hamiltonian, because of the map, you get this parabola. This is the Hislop-Longo result, T00. This is for the ground state in the infinite single interval in the infinite line. The case I want to study is this one, finite temperature. So single interval, finite, infinite system, finite temperature. You play with the map. This is the map, the beta, and you see the beta, what is called entanglement temperature somehow, this function is more complicated. But if you calculate the length of this cylinder, you get exactly the formula of Calabrese-Cardi plus this correction. And then this is the observation of Calabrese-Cardi saying, look, at high temperature, you get the thermal entropy. Well, but now we want to go beyond, use these objects. So one thing is to introduce this, what is called by Chen and Vidal contour, which is just, there are properties that they define, but in the end, they want to capture the spatial structure of entanglement. And it has to do something to do with our approach, because if you now look at your modular Hamiltonian, if you now look at the prefactor, which I call beta in general, it turns out that this is just a geometric fact that the length of this cylinder is precisely the integral of this f prime. And then it's natural to say, look, then I have a candidate from, if I know this f prime, I have a candidate for the contour function. So this is just candidate for my spatial density of entanglement. Okay, you might say this is not correct, but you go to experiment, whatever experiment, go to numerics. If you calculate on a harmonic chain this contour, you find this collapsing of the data, and then the dashed curve is the CFT curve that is completely overlapped. And you see here at zero temperature, it tells you that what we know that from the boundary you get the largest part of entanglement. No, it's this divergent. This is just the inverse of a parabola. So the fact that the parabola do like that, 0L, x, L minus x over 2L. If you do 1 over this, the fact that these are 0, create this linear divergence here, and if you integrate 1 over x, you get the log. That's the origin of the log here, in this contour approach, let's say. You can play also the case of finite temperature. It's more complicated, but situation is, here is the function, and here is the other function that gets the data. Now, what happened? Now let me go to the Bisoniano-Wickman theorem. What has this something to do with? So this is a Bisoniano-Wickman theorem, and then in CFT, Minkowski spacetime, and in the ground state. No, take 1 plus 1 for simplicity. This is the action of delta inside the diamond, and then if you act with J, you go outside. Now now there is a interesting part. This is Lorentzian, T and X, and if you now study this modular evolution here in the Euclidean means that you have a time. Now you have a time. No, you have tau, delta I time. Tau is a time. Now you go to tau I theta. You go to Euclidean modular time. This flow inside here becomes this. It's analytic continuation. But now there is, look, interestingly, what does this flow do? The red thing is the interval. The blue is the complement. If you follow the flow and you stop at half, you go in B. Okay? While here, if you follow the flow, whatever you start, you end up here. You don't go in B. You need J to go in B. Okay, but then if you calculate, take the simplest case when A is minus BB, T equals 0. If you start from a point X here, this is B minus B. If you calculate this point here, is just the inverse, very simple thing. Sorry? Yeah, I have the pointer. Right, sorry, but yes. Okay, that's the thing. But now, this is in the ground state. Now, if you play the same thing at finite temperature in CFT, you know that you have a thermal cylinder, no? And then here something funny happens, because then if you write these modular flows on the cylinder, you discover that if you start from the end point here, you go close to the end point. But if you keep going, at some point, you go to infinity. And this means that if you want to go from your interval to the complement, some part go to the complement, but some part, which is the green part, goes behind. So you have to think that you are in a cylinder like that. This is your T equals 0, whatever it means, slice in the Euclidean. you have your interval. So sometimes look that, sometimes tack, you write to infinity, and then what happens here, you go behind in the second copy, okay, because this yellow line captures the entire line here. So at finite temperature, the modular trajectory provides an interval, alpha beta, the green part, which mapped to the other side of the cylinder, right? And now, interestingly, if you calculate the contour from the modular Hamiltonian on this green interval, you find exactly the thermal entropy at any beta. So that's my first example. And the message is that, okay, if you just keep entanglement entropy, you go to large temperature, you see the thermal entropy. If you use also extra information with modular J, contour, blah, 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 you find thermal entropy at any temperature. Of course, at large temperature, what happens? That your cylinder becomes very small, and the green interval becomes the entire interval. And this you see from the formula. But this is the simple. Right? What happens at in Minkowski, because this is Euclidean Minkowski. This is your diamond in Minkowski. This is the green area that you can construct. And then you draw some modular trajectory here, and you play with J. Yes, you find that in this case, this piece is mapped here, this piece is mapped there, and the green part, yeah, you notice that this trajectory do not cross the green part. But if you do cross the green part, only this part, span an entire Minkowski space. Yeah, this is the property of the map. But if you want, this is okay, because if you expect this thermophile double description, well, basically you have a copy here, and another copy in the other side. Schroer call it second word, just because you have a mixed state. You start with a mixed state, not with a pure state. No? At the level of entanglement, at finite temperature, this is not true anymore. No? And here you see explicitly, because there is this region that is mapped in the second word. Right. So these are the modular trajectory, and this is the causal diamond associated to the interval that I showed before. Yes, this is the action with J of this. Yeah, here I cheat a little bit, because from the map it seems that this Cian part becomes complex, and I don't know what to do with them. But this part goes here, this part goes here, this part goes here. And if you enter, the green part goes this one. There is a plus IB, just a phase to cancel out, but there is an imaginary part constant, but the real part span an entire Minkowski. Where from? Yes. Yeah. No, sorry, but this one, this green, you mean? This one, sorry, this, if you take this green, right, and you map it, you get I pi over 2 plus a real part. So this is not in this space, it's in the other. You have to think that there is Minkowski. First Minkowski, where your diamond lives, blah, blah, blah. And then there is second Minkowski, which corresponds to the second copy in Euclidean behind, that is captured by the green diamond. That's the message, yes. Yeah, yeah, this, what I say is that this is the modular, yeah, if you take this, you modular conjugate, this part goes here. Then you go in other somewhere else that I don't know, but this part has a real part which depends on x, but a constant imaginary part that does not. You cancel out. Yeah, I'm running out of time, so maybe. But right?
Covering the thermal entropy.
Yes. Length, finite beta. Yes.
I don't understand that. Like when you started like the discussion today, you said, okay, a large beta, small beta, infinite temperature. You would get the thermal entropy, and then there will be like corrections. Do you also like? I don't know what it means here to get like an equality. There's no dots.
No, yes, that's right. Because if you want. If you want this function, this contour function is the one that I take from Ka, no? 1 over f prime of x t0, 0. So I take this, but in principle I could shift by a constant. This is an arbitrary, no? Because yeah, I didn't stress enough. These contour functions are infinitely many in principle, because in the end you want to recover the entanglement entropy as a density. So an area, if you give me the area, is 5. How many functions? I get infinitely many. This one is a candidate. And if I use that, I find this property. But in principle, I could say, no, I don't like this C. I change this, but this contour function is suggested by. Yes, here you integrate on the green. That's why it's finite. Not the full. If you do it on the full, you get the entanglement entropy. Yes, yes. If you do this, the same function, you integrate on the red, you have to regularize because it's otherwise divergent, and you get the entanglement entropy. But if you restrict to this green function, which is natural from this modular J, I'm not saying an observation, you find the thermal entropy. Yeah, it sounds weird, but yes, but if you don't mind, I will skip completely the SCFT part. But yes, let me say that there is one can relate this to the bit threads, but I want to go to the last part. If you want, ask me in private. There is an ADS story behind this J in higher blah blah blah. Sorry, but I want to go to the last one. Yes, which is related to entanglement Hamiltonians on the lattice, because it's related to these transitions that I want to tell you. So take your lattice, harmonic chain, so the simplest lattice model you can think about. Right, this is momentum, position, this is the mass, this is the frequency, this is a spring-like interaction here. Well, take the ground state. So the ground state of this model is quadratic. The theory is Gaussian. You can use Wick theorem. So you can do a lot of things. Okay. In particular, you can calculate this operator, entanglement Hamiltonian, which is quadratic in QMP, and can be written in terms of the two-point function restricted to the subregion. There are explicit expressions of this V and T. This V is the standard potential and kinematic term here, because V multiplies Q, T multiplies P. There are explicit relations between this two-point function, QQ and PP, and this V that are not very insightful. That's why I'm giving this relation for fermion, which is easier. And so if you play around with fermions, you can do the same thing. And now this is the special formula that relates the two-point function restricted to your subsystem to this matrix T. This you can calculate. And the point is that this one, so in general, this matrix T, so this is a quadratic Hamiltonian, but typically this T is fully populated. So it's not nearest neighbor, but it's long range and inhomogeneous. So terrible object. In the lattice. Because in the lattice you see this Hamiltonian is a quadratic Hamiltonian, nearest neighbor. So if you write it in this form, T is diagonal. Actually there is next to nearest, so it's only one term and then constant. When you do this, you obtain still a quadratic, so it's good, but this T matrix is a mess. Okay, so and then it's a problem how to go to the continuum with this messy matrix. This is an example. If you change the mass, very small mass, this is the matrix T, see, 10 to the minus 30, massless, fully populated. You keep increasing the mass, and there is something interesting happening. From being non-local, fully non-local, it becomes local, where at large mass. No, this is a numerical thing. You put it on a computer, you calculate, and you see the density matrix. You see what at large mass, you are left with three diagonals here, basically the main one and the next to the other one, which are non-homogeneous. You see, so that's the main. I want to go to large mass regime because this one is difficult. This one is even more difficult in the middle. This one is easy. So I want to. So here I can say something. If you go the other matrix, the potential, same phenomenon. Go to the large mass, becomes. So this is massless. It's kind of localized, but then there is interesting this anti-developing. Then shrink goes to local again. If you now look at what happens on the diagonal, so this is TII, VII. For small mass, it's something like that. For big mass, it becomes a triangle. These slopes are known analytically from Peschel formula and corner transfer matrix approach that Frank was mentioning before. So, so the message is that, okay, at massless regime, there is a whole story that I will not tell you, but in the large mass, this big matrix, fully populated, becomes local, and not only local, but the shape is very simple, it's a triangle, okay? That's what we call a three diagonal approximation. So only these diagonal are non-vanishing, and the slopes are known from the corner transformatic approach. Okay, now.
Small mass regime, previous slide, it looked like
Here.
Maybe it's just a 12 scheme.
Yes.
It still looks, but yellow is not very different from red.
Yes, I agree that these are very small, very small elements. But if you forget them, you don't get. Yeah, it's a lot. But if you forget them, you don't get in the massless regime. You can do analytical equation for fermions, and if you forget this, you don't get the parabola. It's another story, but. Yes, let me stress that these are important, very important, even though they're very small. If you sum over all of them, you get a parabola. If you just study the diagonal, yeah. Sorry, but we can discuss. This is an interesting question, but how you get the. But now I want to be simple because I want to go to this transition. Because I just want to stress the large mass regime is simple. This is what you expect, because if you go crank to large mass, the correlation length is basically 0. But here you see something non-trivial, because, okay, this you expect, no? Because this slope is dictated by what happens at the single endpoint, no? What I'm saying is that, so Peschel in the 90s with the coordinate transformative mesh calculate the Bisoniano-Wickman case, no? And he found the linear thing. And he found the slope of these things using coordinate transformation. Now the observation is that if you do the same calculation for the interval, not for the half line, well, at very big mass, everything is dictated what happens here. And so you expect the same slope and the triangle, okay? And indeed, numerically, it what happens. No? Omega 10, you find this triangle with the same slope predicted by Peschel. Now what happens, and this is the last part of my talk, what happens if you have two blocks, no? In the spirit of the transition that I was mentioning in the beginning. Take two blocks, okay? Take two blocks like this, equal for simplicity. So this is the matrix. This is for two intervals. This is first interval, second interval, for small mass, okay? For big mass, you see that here matrix fully populated. For big mass, omega 3 goes here. If you go to big mass, it becomes diagonal again. But what happens on the diagonal? Well, now you guess, no? You say, okay, for very large distance, the interval do not see, no? So you expect two triangles. But when they are attached, no? These are the two triangles where the interval is twice. So you expect a big triangle. No? Okay, what happened in between? So how do how I go from two disjoint triangle to a single big triangle? This way. So these are the numerically for big mass, the diagonal. At some point, this triangle breaks, and this wedge increase, the other wedge decrease. But you see, there is a critical distance where this triangle becomes this shape, no? And the other symmetrically. Yes. Yeah, let me explain. This is the main last thing. So here I'm plotting the diagonal of the entanglement Hamiltonian. Only the diagonal in the large mass regime. And then I vary the distance. These are when they are attached, and these are when they are very far away. So when they are very far away, they are here, they don't see each other. And so I see the two triangles, the gray one, this and this. And then I decrease the distance from infinity, large, to 0. And here I arrive to this delta. This delta is d over L. This is L. Okay. No, I'm not going to say that. But I'm happy you say that. No, but of course it's an analogy, but this is an opposite regime because it's supermassive. And no, let's say that, okay, there is a difference because this is for equal intervals. There you can use CFT and you can. But here, at least, let me stress that you can say, yes, but what is the, what do I get beyond the single interval case? No? That I cannot read from the single interval case. Well, this you cannot read the transition, why it happens at 1/2. So if you ask me, this is a geometrical problem. How from two triangles you merge in a single triangle. You can do it in many ways, depend on the velocity. This is a way, but in principle it can break at infinity, craze, or you cannot break at all, arrive here, and then immediately. So then you do the numerics, you discover that there is this critical distance. And you say, why? Wait, why this is beyond? Because if you plot the entanglement entropy, you see nothing, you see constant. This is supermassive regime. So you see flat thing because you see only what happens close to the endpoint. It does not even depend on the geometry. Small mass, no, because everything is everything is spread out. Yes, so this is a feature, of course, of large mass, but yes. In the vacuum, yes. Then you look at the spectrum. The spectrum, you say, okay, the spectrum is something between. And there is something happens also here, because in the spectrum, single particle entanglement spectrum, this is where they are attached. You see the what I want to stress here, what they are attached here, no? Is a single interval. The degeneracy here is 2. While we are very far away here, the degeneracy is 4. Look at the point, because there are 4 points, 1, 2, 3, 4. Then you keep increasing. Here you arrive at the critical distance, and you start developing 2 slopes like that, where here the degeneracy is 4, here the degeneracy is 2. This I don't understand, but this is numerically what happens. And then, yeah, this is the end for equal interval. And then you say, okay, if I move, take these different intervals, interesting, because now, it's geometric problem, again, more complicated, because now you have to merge 2 different triangles into a big triangle, like that, of 2 different bases, no? And then you say, how it happens, no? And then you do the numerics. Rho here is the ratio between the length, and you see that there are three critical distances. Here, for instance, you arrive from infinity, then you get this shape, and then this is the other shape, and then they break, and then they create a triangle. So it's interesting because in this case, somehow it tells you that the final triangle is made by, this part is made by the left, and this part is made by the right. If instead you have a bigger thing, no? This tells that in the final triangle, this one, so only a piece of it is made by this, while the other piece is made by the big one. Crazy, yes. I don't understand, but yes. And then there is also a critical value of the ratio, something such that this happens. But then you can say, okay, there are 3 critical distances corresponding to these different geometric picture that you find, which are these one. You see, for L1 equal L2, they all becomes L1. They squeeze. And this is the numerics, just to tell you that no cheating. Also the spectrum, see something like that. Let me conclude with we have this heuristic interpretation of why this critical distance emerge. Well, so these are your 2 intervals. Think, for instance, they are equal for simplicity. You can say, assume that somehow this point influence this region here, and this other point influence this region here. When they are far away, the area of influence, whatever it means, they don't touch. At some point they touch. This is what happens, no? Where they are very far away, at some point they touch, and you start penetrating the region, the domains here. And this is precisely where the first transition happens. But then you see, the gray part. So, yeah, this is the generic case, but if you think to the simpler case, when they are equal, it's simpler, like this. So simply when they touch, they start, this is where the critical distance happens, like that. So when they are different, somehow the biggest interval knows about the smaller interval in this way. You draw this, and then you predict these critical distances in this geometric way. It's a very naive picture, but it works. And then in the massless regime, this is what happens. It's a mess, but you can see some front. Yes, and yeah, we will conclude, because the massive regime, yeah, it's still an open problem in the continuum, the massive. So what is the modular Hamiltonian of a massless scalar for 2 intervals? Nobody knows. This is the numerics from from the lattice, very small mass, and you see everything is populated. You can see this front that we know analytically from the fermion case, but yes, if you want, somebody want to discuss. So this is the end. This is what I told you. There are many open problems. If you change the spatial configuration state, if you go higher in dimension. I didn't talk about the bit thread story, but yes, and you can go out of equilibrium. And then let me advertise this event we are going to have in Trieste next year with algebraic quantum field theory people. So if you are interested, please stay tuned. Thank you. Yeah. Which one? Stop me. Which color? Entanglement matrix. Ah, yes. The entanglement Antonian matrix. Okay, sorry. And on the lattice, you mean, right? Yes. Sorry. 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 Yeah, I completely went over time. Yeah, sorry. Okay, which one? This one, right. Here? No, here. So you see here is just a density plot of the matrix of the element. Of course, you cut because here otherwise the main diagonal is too big, and you don't see what happens. But so, no, here there's no transition. Here the mass is too small to have some. What I want to show in this plot is just if you crank the mass to big omega, you becomes local again. That's the meaning. But in the middle here, I don't know what happens. Analytical, it's just a numerical thing that you see, yes. Yes. No, look, this red could be an effect of the cut. Because you have to imagine that you have, it's a 2D, if you imagine that you have this matrix, this is the main diagonal, which is very big. You have something along the diagonal is very big, and then you cut at some point to see what happens here, small fluctuation. And if you cut, it's clear that this part, you know, so it can be that. Yeah, here we keep the same range just to show you that when it's white, it's really 0. When it's yellow, yeah, it's not 0. And you have to keep it because if you work with the fermions, massless fermions, something similar happened, but it's analytically under control. Peschel and Dessler study the subdiagonal in the thermodynamic limit. There are analytic formulas. Maybe I have. No, I don't have. And then you can do the continuum limit, and it turns out that this is very important. This part is very important if you want to go to the continuum. Otherwise, there's no way. If you just restrict to the main diagonal and the next one, they know the expression, and it's an hypergeometric 3.2, but it's not a parabola. If you want to recover the parabola, you have to sum many hypergeometrics, then you get the parabola. And this is the harmonic chain example because, yes, but in principle, yes. But the message is that both fermion, there are similar plots for fermions that, again, if you go to big mass, you recover the triangle. Of course, different slope, that again was found by Peschel, a corner transform. But that's the meaning of this plot, is just the fact. Yeah, I would be happy to know what happens here. Yeah, because even in this case, there is no analytic formula in the continuum. There is here a small mass, and maybe here infinite mass, but in the middle, yeah, very likely it's non-local, fully non-local, but it's still an open problem. Yes, please ask me whatever we want. Okay.